All right, now let's say something about the convergence rate of the bisection method. Okay, so let's state the theorem. So let f be continuous in some interval, and suppose that the function changes signs. Changes sign, it's like over the interval. F of a times f of b is less than 0. Then the bisection method generates a sequence let's call that alpha n, which converges to a root alpha with the property that alpha n minus alpha in absolute value is bounded from above by b minus a over 2 to the n is greater than or equal to 1. Okay, so the proof is relatively straightforward, right? So the claim is that for each n, there is some root alpha which is contained in an bn, right? And that's just by a consequence of the intermediate value theorem sort of repeatedly applied. And then we know that alpha n is 1/2 an plus bn, so it's the midpoint of that interval. Okay, so the worst case, right, is that the difference between alpha and alpha n. So alpha is going to be somewhere in this interval from a to b, right? So an to bn. So alpha is somewhere here, and we know alpha n, which is the midpoint, is this midpoint here, right? Which is an plus bn over 2. So the maximum distance, it's like alpha n can be from alpha, which is anywhere in this interval, is half the length of the interval because, just by observation, right? So this is going to be less than equal to bn minus an over 2. But we know that each time you apply the bisection method, the length of the interval decreases by a factor of 2. So bn minus an is equal to 1/2 bn minus 1 minus an minus 1. And so eventually you get 1 over 2 to the n minus 1 b minus a. Okay? So that tells you that alpha n minus alpha, right, is less than equal to okay, so we have this. So that's less than equal to 1/2 bn minus an, but this is equal to 1/2 times 1 over 2 to the n minus 1 b minus a, which is just b minus a over 2 to the n, which is what we wanted to show. Okay, so that's sort of a relatively straightforward proof that the bisection method converges. It's like at this rate, which depends on sort of decreasing. It's like the sort of the length of the interval. It's like by a factor of 2 for every iteration. Okay, all right. So that's not such a big deal, but you know, it's nice to know that you have a method which is guaranteed to converge at at a rate which is basically one binary digit of accuracy for every iteration, which is not very fast. There are faster methods which we'll discuss in a little bit, but those Foster methods aren't necessarily guaranteed to converge. Okay, so you can ask yourself, well, okay, we have a method which gets closer and closer to the right answer in some appropriate sense. How do you decide when to stop the method? Okay, so this leads to the question of stopping criterion. Okay, so there are several ways to do this. One possibility is to look at the absolute error. So you stop when sort of the absolute difference between alpha n and alpha is less than some tolerance. Okay, so by the analysis we had done before, we know something about this. So it suffices to guarantee that if b minus a over 2 to the n is less than this tolerance, then I can choose an n for which alpha n minus alpha in absolute value is less than the tolerance which I give you. Okay, so that's one possibility. So another possibility is to look at the relative error. So I could stop when, say, alpha n minus alpha over absolute value alpha is less than the tolerance. Okay, and you could write this in the following way. You could have b minus a over 2 to the n less than the absolute value of the nth iterate, right? So you don't know what alpha is, so in order to make it computable, I'm going to replace alpha by alpha n, and that's usually a fairly reasonable approximation. Okay, and so I could have a stopping criterion which is based on this condition here, and this would give you something which approximates the relative error. And then there's one other possibility, which is what the function value at alpha n is. So this is what's called the residual error. So the condition, or the defining property at the root, is that the function value at the root is equal to 0. So you can evaluate the function value at the iterate and see whether or not that is close to 0. So that's another possibility. So you can look at the absolute value of f at alpha n, and you want that maybe to be less than some tolerance. Okay, so those are some possibilities. So let me give you an indication of, well, what are some of the possible things which where these various methods are good or not so good. Okay, so let me give you an example. Okay, so say you have this kind of function, which gets the value of the function is very small for a very long interval, right? And then alpha is the root. Okay. So for these kind of things, conditions 1 and 2, which have to do with the error in the actual position of the root, right, are good. Right, they give you a very good location. But this residual error is not going to be so good, right? Because, over a very long interval in sort of candidates for alpha, the residual error is very small, right? So if you would just rely on the residual error, you would have terminated its like pretty fast, even though you were actually quite far from the real root. Okay, so that's one possibility. Another possibility is sort of the other extreme, right? Where the function changes value very rapidly through that. So in that situation, both 1 and 2 are potentially bad, because even if you get sort of close to it, you could have a very large function value. And so usually some combination of the two is important, is sort of the take-home message. So whereas 3 here would be good. And so the take-home is that so you should test both so absolute or relative error and the residual error. So the point basically is that these three error measures are all measuring different things. It's like, and again, depending on the application which you have in mind, it's like, you know, all of them are potentially relevant. And so you might want to set stopping criterion which involves some combination of all three of these things, right? So maybe you only want to stop when all three different stopping criteria are satisfied, okay, with different tolerances, possibly. Okay, all right, so let me just stop here for now.